Today I will be starting with the valence bond theory. As you know that this theory was used mainly to explain the shapes of the molecules and the directions of bond in them. It was given by Heitler and London in 1927, and later on it was extended by Pauling and Slater. Now let us talk about the main postulates of valence bond theory. According to that, covalent bond is formed by the overlap of valence shell of two atomic orbital, and that is why it is known as valence bond theory. Each of the overlapping orbital, they will contain unshared electrons of opposite spin, and each of the bonded atoms, they will retain its own atomic orbital, but the electron pair in the overlapping orbital is shared by both the atoms. And in this case, two types of bonds are formed. One is the sigma bond, which is formed by the sideways overlap, and other one is the pi bond, which is formed by the parallel overlapping. Let us see the example of the sigma and pi bonding. Now this 1s orbital of hydrogen, they overlap sideways, resulting in the formation of sigma bonding. While the p orbital of oxygen, it overlaps, this overlapping, that will result in the sigma bond, while this overlapping, that is the parallel overlapping, it will result in the formation of a pi bond. Now let us compare it with the molecular orbital theory. It is another approach to explain the formation of covalent bonds in the molecules or the ions, and it was mainly developed by Hund and Mulliken, and later on it was refined by Jones and Coulson. So it is also sometimes known as Hund-Mulliken theory, and this theory is also known as LCAO theory, that is linear combination of atomic orbital theory, since the atomic orbital it combines in a linear fashion. Now let us try to understand the postulates of molecular orbital theory. In this, what will happen, the atomic orbitals, they will overlap, resulting in the formation of molecular orbitals. And atomic orbitals, when overlap, they form two molecular orbitals. One will be the bonding molecular orbital, which is at lower energy, and the anti-bonding molecular orbital, which is at higher energy. Now each molecular orbital, like an atomic orbital, they can accommodate two electrons with opposite spin, and depending on the overlapping, it can be sigma, pi or delta. And while filling the electrons in various molecular orbitals, they will follow this three principle, that is Offer principle, Hund's rule and Pauli's exclusion principle. And let us consider in terms of waveform, if psi1 and psi2, they are the waveforms of two atomic orbitals, and during the linear combination, the molecular orbital, that will be the constructive overlap, resulting in the formation due to the summation, and anti-bonding molecular orbital, that will be due to destructive overlap, that is due to the subtraction. Now here I am showing which one is the constructive overlap, which one is the destructive overlap. So in this case, when 1s orbital, they are combining with this positive sign, that results in the formation of a constructive overlap, that is, they are having same wave character. In this case, this 1s orbital of H and 1s orbital, this one is orbital of H, when they are overlapping, they are resulting in a destructive overlap. So one is resulting in the formation of bonding, another is resulting in the formation of anti-bonding molecular orbital. So bonding will be shown by this sign, and for anti-bonding we are using star sign. These are the two formula for filling the number of electrons. So up to 14 electron system, that is from hydrogen up to nitrogen, we are having 14 electrons. We will be following this pattern, that is sigma 1s bonding, sigma 1s anti-bonding, sigma 2s bonding, sigma 2s anti-bonding, and pi orbitals. This bracket shows these two, they are having same energy, then sigma 2pz. Now there is repulsion, due to which this orbital, it is shifted to a higher energy order. Then anti-bonding of this, that is due to the 2s 2p interaction, this is pushed to higher energy level. After 14 electron rule, everything will remain same, only difference is that this orbital, it will come here. So sigma 1s bonding, sigma 1s anti-bonding, 2s bonding, 2s anti-bonding, then 2pz, sigma 2pz will come. Here it was shifted to higher energy order, but here it will come with S. and then pi orbital and pi antibonding of this two. So this is how the filling of electrons will occur according to the MO rule. Now I will be discussing the molecular orbital theory in detail, and in my next video I will be discussing about the valence bond theory. So how according to the valence bond theory we will predict the shapes of the molecules. So let us come to the molecular orbital theory. As you can see in the diagram, this rule is up to the 14 electron, and this is after 14 electron rule. So up to 14 electron, first pi bond will come and then the sigma bond here. After 14, first sigma bond will come and then the pi bond is there. So this is the difference in the filling of electrons in 14 up to 14 and after 14 electron rule. Now let us talk about the bond order. That will be the number of electrons in the bonding orbital minus number of electrons in the antibonding molecular orbital divided by 2. When we talk about the magnetic properties, they are judged on the basis of number of paired or unpaired electrons. If the electrons they are paired, that will be known as the diamagnetic, and if they are unpaired, so it will be a paramagnetic behavior. Now let us compare the valence bond theory and molecular orbital theory. In both the cases, they show the distribution of electrons. Whether it is atomic or molecular, it cannot have more than 2 electrons. Both the theories include the sharing of electrons by the nucleus, and according to both the theories, the energy of overlapping orbital must be comparable, and there must be some similarities in their symmetry. Now let us discuss the LCO method, that is linear combination of atomic orbital method, which takes place by addition and subtraction of the wave functions of atomic orbitals. So when the wave functions they are added, that will result in the bonding molecular orbital, and when they are subtracted, it is forming the anti-bonding molecular orbital. So you can see in the diagram, when there is constructive overlap, that will result in the bonding, and when there is destructive overlap, that will result in the anti-bonding. This is the general view, that is two atomic orbitals of same energy when they are overlapping, that will result in the formation of molecular orbital. Now this in between region is that of the molecular orbital. This one is the bonding molecular orbital, which is at lower energy, and that will be the anti-bonding molecular orbital. Now in this case, since s orbital overlap is there, that will result in sigma bonding and sigma anti-bonding. This we are discussing the molecular orbital of H2. So this is the atomic orbital of H, this is atomic orbital of H. And now since H it is having one electron, so 1s1, 1s1. So one electron you will be filling. Now when molecular orbital is formed, that will be, since s orbital is there, so constructive overlap will result in sigma bonding and destructive overlap will result in sigma anti-bonding. Now this will be filled according to the of-phase principle, Hund's rule and Pauli's exclusion principle. So lower orbital it will be filled first. So in bonding orbital there are 2 electrons, in anti-bonding orbital it will be vacant. So when we will be finding the bond order, that will be half number of electrons in bonding it is having 2 electrons, and number of electrons in anti-bonding. So bond order will be 1. Now this is the molecular orbital diagram for boron, diboron. So boron, since it is having 5, atomic number is 5, so configuration will be 1s2, 2s2, 2p1. So 1s I am not taking, I will be starting with 2s and 2p. So this is a 2s orbital and this is 2p orbital. Now in s there will be 2 electrons. It should be 2. Similarly here also it will be 2. So first total will be 4 electrons. So first the bonding molecular orbital will be filled and then the anti-bonding molecular orbital. Now in p that will be 2p1, because the configuration is 1s2, 2s2, 2p1. So 1 electron in each of the boron atom. So when bonding will occur, the molecular orbitals it will be as per the 14 electron rule, that is the pi orbital will come first and then the sigma orbital. So this 2 electrons they will be occupying the 2 pi orbitals. Now in this case, when you are finding the bond order, that will be half number of electrons in bonding. Bonding is 2 and 2 4, or you can take 6 also if you are considering 1s. So that will be 4 minus 2. So it will be 2 upon 2, that will be 1. So bond order will be 1. So when you see the magnetic behavior, since unpaired electrons they are present in the molecular orbital, so it will be paramagnetic in behavior. Now let us consider the MO diagram for nitrogen. Nitrogen, as you know, it is having 7 electrons, so N2 will be having total 14 electrons, so it will be following the 14 electron rule, that is pi orbital will be coming first and then the sigma. So the configuration will be 1s2, 2s2, 2p3. So s orbital I am not taking, I am starting with the 2s and 2p. So 2s2 means 2 electrons in the 2s orbital and 2p3. So in px, py, pz you will be taking 1 electron, because first it has to be half filled. Similarly for the second nitrogen, 2s2 and 2p3. So when the orbital will overlap, that will result in the formation of 2s bonding and 2s anti-bonding. So total 4 electrons are there. So 2 will be in the bonding, 2 will be in the anti-bonding. Now in this, first 2 pi orbital will come and then the sigma orbital, since it is following the 14 electron rule. So total, if you see 3 plus 3, total 6 electrons are there. So this 6 electrons you have to fill here in between. So one orbital can accommodate maximum of 2 electrons. So first you will be half filling it and then pairing will occur if electrons are there. So total you are having 4 electrons here. Now what is left is 2 electrons. So this 2 electrons, they will go to the higher orbital. So when we find out the bond order, that will be half number of electrons in bonding. Bonding is 2, 2, 4, 5, 6, 7, 8 minus number of electrons in anti-bonding, that is 2. So you are getting 6 upon 2, that will be 3. So bond order will be 3. Now if you see the magnetic behavior, since all the electrons in the molecular orbital they are paired, so it will be dimagnetic in behavior. Similarly you can find out for N2 minus. N2 minus means 1 electron you have to add, so you can add this side or that side. So 1 electron when you are adding, so that electron will enter here. Then there will be change in the bond order, so it will be half number of electron bonding, that will be 2 to 4, 5, 6, 7, 8 minus number of electron in anti-bonding 2 and 1, 3. So you are getting 5 upon 2, that is 2.5 will be the bond order, and the magnetic behavior will be now paramagnetic, since one unpaired electron will be here. Similarly you can find out for N2 plus also. Plus means you can remove 1 electron either from here or from this side. So when you are removing, 1 electron will go from here. So then you can calculate the bond order, that will be number of electrons bonding, that will be 2, 2, 4, 5, 6 and 7. 7 minus 2, you will be getting 5 upon 2, again 2.5, and it will be paramagnetic. So this is how the bond order, the magnetic behavior, it is calculated. Now let us do of HF. HF is having some exceptions. So since it is not following the 14 electron rule, in this case now hydrogen is having 1 electron, 1s1, which I have shown here, and fluorine it is having 9 electrons, that is 1s2, 2s2 and 2p5. So 1s I have not taken, so this is 2s and this is 2p. So 2s2 and 2p, 2, 2, 4, 5. Now in this case, when overlapping occur, these electrons which are paired, they will not take part in the bond formation. So these electrons I have shown here in colored form. Similarly this electron I have shown here, they are non-bonded electrons. The overlapping will be between this unpaired electron of 2p and unpaired electron of 1s, resulting in a formation of sigma bond. So when we calculate bond order, that will be half number of electrons in bonding. Bonding is having 2 electrons, so 2 minus anti-bonding is having vacant, so 2 minus 0. So you will get bond order to be 1. So similarly you can find out for HCl also. It also shows exception. So till now we were doing the homonuclear molecules. Now let us start with the heteronuclear, that is carbon monoxide. These are the atomic orbitals of carbon, and these are the atomic orbital of oxygen. Now oxygen being more electronegative, you will be drawing the energy level little bit at lower energy as compared to carbon. So carbon is having 6 electron, that is 1s2, 2s2, 2p2. So 1s I have not shown, this is 2s and this is 2p2. Oxygen having 8 electrons, so 1s2, 2s2, 2p4, 1s I have not shown. In 2s there are 2 electrons, in 2p there are 4 electrons. So when overlapping occurs, this 2s will result in bonding and anti-bonding. And in this case it will be following the 14 electron rule. So first pi orbital will come and then the sigma orbital. Now what you have to do is, total you have to see 4 plus 2, 6 electrons. So 6 electrons you have to distribute here. In 1 electron you can accommodate more, as you know, 2 electrons only in 1 orbital. So first you will be half filling this, then you will be doing pairing. Now after that only 2 electrons are left, so it will go here. So this is how you will be calculating. Similarly you can find all they are paired, so it will be dimagnetic in nature. Di means 2, paired, and bond order will be half number of electrons bonding. You can calculate 6 and 2, 8 minus anti-bonding 2. So you are getting 6 upon 2, that will be 3.